In this video, I want to run through some tips on setting up the Newton's rings experiment. There are two pieces of glass, one with a flat surface, and this one, the one on top, has a curved surface resting on top of the flat surface. If you imagine the bottom curved surface here, this surface, to be part of a sphere, what do you think the radius of curvature, or the radius of that sphere would be? What do you think the radius of that sphere would be? It's not going to be 10 meters. It's less than 10 meters. But it's going to be more than, say, 1/10 of a meter. So when you measure the radius of curvature of that bottom curved surface, make sure that you do a sanity check on the number that you come up with. If it's 10 meters, then you're probably wrong. So light is going to come directly down on top of this lens, on top of this piece of glass, and we'll see what happens to the light in theory now. So what's happening in this experiment? We have a piece of glass on top with a spherical surface lying on top of a flat piece of glass. Sodium light is shining from directly above. The waves look like this, or a single wave train looks like this. A ray of light comes down, straight down through here. There's the normal, bends away from the normal there. At this interface, part of it gets transmitted through, part of it gets reflected. Let's just draw it like that. And then at this interface, the transmitted wave gets reflected. This comes up like that. Of course, it also gets transmitted through, and there's another reflection there, but we don't care about this. You can think about why afterwards. We also don't care about the reflection of this top surface, and you can think about why. So the only two reflections we're interested in is the one from this interface with the curved glass, and this interface with the flat glass. And there's air in between these two pieces of glass. Now, the thickness of the air film is getting bigger and bigger and bigger. If you travel away from the center, it's getting bigger. Now that means that since these two rays are actually a distance apart because of the geometry and Snell's law and all that, they travel a different distance. So when they come back up, they're a bit out of phase. They started off as one ray, but they end up being a bit out of phase. And when your eye combines the two, the eye sees interference patterns. So it might see a dark ring there, a dark ring there, dark ring there, dark ring there, dark ring there, dark ring there. Because this is a spherical surface, you actually see rings, dark rings or light rings, depending on how you want to look at it. And they are concentric because with the center being this point here. The other thing you'll notice is that the rings get closer and closer together as you move further away. and you can think about why that is. It's pretty obvious, but you can think about it anyway. But there's something more going on than just a reflection there and a reflection there. If you look in the middle, you might just see a black spot there. And the question is, why does that black spot appear? If this is pretty close to being spherical, and this is pretty close to being flat, then you should have a very tiny, almost infinitesimal air gap in between there. So the light that reflects off the curved surface, there's a ray that comes straight down, hits the middle, part of it gets reflected off the curved surface of the interface, part of it gets transmitted through a tiny air gap. Tiny air gap. But there is an air gap. Tiny air gap. And it gets transmitted through the air gap and gets reflected off the top of the flat plate. Gets reflected off the top of the flat plate, and yet you see a black spot there. Well, there's virtually no path difference between the top reflected ray and the bottom reflected ray. There's virtually no path difference, and yet there is still a black spot there. So why is that? Well, there's something more happening at this bottom interface. The thing is that if you look at the refractive indices, and this is some refractive index NG, whatever the glass is, the refractive index of the glass. And this is, let's suppose it's the same type of material, same type of glass, the same refractive index, Ng. In between here, you've got N air, the refractive index of air. Now, the refractive index of air is less than the refractive index of either of these two glasses. The thing is that when a wave passes from a region of large reflective index and it reflects off the interface with a substance of smaller refractive index, then there is no phase change at this boundary. The light simply reflects. But at this bottom interface, the light is coming from air and impinging on an interface with glass. So in that case, it's going from a region of low refractive index to high refractive index, and reflecting off that surface, and then there's a 180 degree phase change. So that's why in the center, you should just see a black spot. So there is destructive interference, even though there is no path difference, or almost no path difference between the two rays of light. Between the ray of light that's reflected off the curved surface and the ray of light reflected off the flat surface. So, the three properties of waves that you observe in this experiment are, well, reflection, refraction, interference. That's three already, but there's one more. Phase change, when light reflects at a boundary, going from low refractive index to high refractive index. So that's what's going on there. So you might like to think about why we don't care about the reflection of this top surface here. You can ask your demonstrator, hassle your demonstrator about that. And you can also think about why we don't care about the light that is reflected off the bottom of the flat plate. The only the only two reflections that matter are the ones off the inner surface of the curved surface of the spherical, half spherical lens, or whatever you want to call it, semi-spherical piece of glass, and the reflection of the top surface of the flat plate. So you can think about that. If you're really keen, you can think about a more accurate picture than this. And the more accurate picture is that actually you have a continuum of rays heading down, all parallel, a continuum of rays heading down, a continuum of rays getting transmitted through here, and they're all, they're doing this sort of thing. A continuum. So if you have your eye here, actually what you're seeing is the sum of all the reflections from all these rays that are coming into your eye. This is a very advanced way of looking at it. But you might be keen to have a look to see if you can make sense of it. You don't have to, you can just see if you can make sense of Newton's rings by considering the reality that actually you have a continuum of rays of light heading straight down onto this two glass pieces of glass system. And you have one observer, your eye here. How does it work? You might like to think about that. And if you can come up with something, tell your demonstrator, and he'd be very happy. He or she will be very happy that they've got a student that's pretty brilliant. Okay, so that's it for the Newton's. Almost it for Newton's rings experiment. I went straight into an explanation in terms of waves, but actually. Newton, who was the first to observe Newton's rings, didn't believe in the wave theory of light. Newton tried to explain these rings in terms of the particle nature of light. And so he had to, no, that's the wrong picture. We know now that that's the wrong picture. But the explanation that he came up with was that the particles of light, or corpuscles of light, have fits and starts as they pass inside this air variable thickness air film. Fits and starts. And that was Newton. Well, hopefully you can come up with a better explanation than that, with the benefit of hindsight of several hundred years of science. I make sure that all the glass surfaces are clean. So you've got two surfaces on the curved glass, the lens. You've got a couple of surfaces on the flat plate here, and you have this surface here, two surfaces there. There could be fingerprints or dust. Just wipe them off before you start. Next thing, after the sodium lamp is warmed up and it's a nice yellow glow, put it so that it's directly adjacent to the microscope. You want the light to come directly out of here and be reflected straight down beneath the microscope, like that. Right, like that. You can bring the light close, as close as you can, adjacent to the microscope. There, I've got it there. Next, you need to bring the glass between the microscope and the lens so that it reflects light straight down. If the microscope is too low, or to adjust the height of the microscope in general, you will need to use this knob here, which moves the microscope gradually down or up. So you can see a little vernier scale there, down or up as needed. You know, if you find that you can't focus the microscope, then maybe it's just too high up and you need to adjust this. Well, it shouldn't happen. Maybe the first group in semester might have this problem, but the rest of the groups probably wouldn't. And of course this knob here focuses the microscope like that. Alright, so let's do this. You want to make this window actually quite narrow. It might seem paradoxical, but that's what you want. Sort of around there. And I'm going to see if I can see any Newton's rings now. The Newton's rings are going to be somewhere, well, where the curved glass is touching the flat plate. They'll be there. They're very small. You can just see them with your bare eye, without the microscope. And I actually just look through the microscope, and with my hand I just move this paper sort of around until I can see the rings. You should be able to get really nice contrast, very bright rings and very dark rings. If you narrow this gap to about maybe 2 centimeters and you have the right angle for this glass reflector, just play with the angle, get the angle right, get the size of this gap right, make sure it's positioned exactly in line with the microscope, and you should be able to get really good contrast with the rings. I can't show you the rings through this video recorder, but the rings look, just from your book, they're going to look like this. Let's just focus in on this. Okay, this is just straight from your book. Let me just zoom in. Chapter 35. This is at the problems in the back of the book. You're going to see rings that look like that, and you're going to put crosshairs in the center of each of these dark lines like this. The immediate objective is to get the radii of many rings. Well, you know, maybe 8 or 9 rings, 7 or 8 rings. You want the radii of 7 or 8 rings. Now, the natural way to do it, or what you would first think of, is to put the crosshairs in the middle of this big black dot, if you can see this big black dot, and just work outward like this. And when you first of all put the crosshairs, right, that's a bad idea. Let me not even continue that thought. What you should do, you see, the thing is that this big black dot is just a blob in the middle. So it's actually fairly imprecise the center, trying to put it, the crosshairs in the center here is an imprecise exercise. It's much more precise to put the, say the crosshairs, let's say in the middle of some outer ring, maybe the 9th ring or the 16th ring. A power of 2 is good to choose, but you can have a few more in between. You can have 2, 4, 8, 16, but you can have ring number 9 as well, and a few others. Put the crosshairs in the middle there of say this ring. Measure the position, or write down the position of the vernier scale on the travelling microscope, which I showed you how to do in another video. And you see, you traverse across diameters. If you traverse across diameters, you can tell pretty well if you're going to go straight through the middle of the rings. So what you do is place the crosshairs of the microscope in the middle of a dark ring, and just shift the whole ring system, the glass, the 2 pieces of glass, so that the microscope is going to traverse an actual diameter. So you just do that before you start measuring anything. Make sure you're going across diameters like that. You're going to sweep across like a whole lot of diameters like that. Making sure that you keep in sequence, write down this position, and this position, and this position, this position, and all the ones that the ones that you actually looked at on this side. The rings, the corresponding ring, well, the same ring. Make sure that you get the corresponding position there. In other words, you're recording a whole lot of diameters of rings. You're recording diameters of rings. So, and of course you record the diameters, and then you divide by 2 to get the radii. So that's just some experimental technique to make it more accurate. Ideally, you should have maybe, as many data points as possible, and then proceed as in the lab manual. So that you should be able to get a good reading, a good calculation for the wavelength of the sodium light coming out of this lamp if you do this. If you have any more questions, you can post them up on the discussion forum, and somebody will answer them in a reasonable time.